Okay, so 6.5 is finding the area between two curves. So in 6.4, we were using definite integrals to help us calculate the area between a curve and the x-axis. So for example, if this was a function f and we wanted to find the area under the curve from A to B, so this area in here, we evaluated the definite integral, so the area was equal to the definite integral from A to B of f of x. And then if we had a function that dipped below the x-axis, so something like, I don't know, like this, where we wanted to find the area bounded between the curve and the x-axis, so this area here, then we had to multiply the definite integral by a -1, and that would have given us that area between the x-axis and the function. But now in 6.5, we're looking to calculate the area between two curves, so between two given functions, either on an interval or an area that's bounded by the functions. Okay, so I'm going to draw a picture here of just two general functions. Okay, so let's say that this is the function f of x, and then we have the function g of x. And we want to find the area between those two curves on the interval from A to B. So we want to find or calculate this area. Okay, well, geometrically, this area is going to be equal, copy and paste this, to the area under F which can be found from evaluating the definite integral from A to B of f of x, minus So minus, this is not working. Okay, cut. But basically minus the area under G. So this area, which can be found by evaluating the integral from A to B of g of x. So the area that in gold here, the area between f and g can be found from taking the definite integral from A to B of f of x, which is the top function in this case, and then subtracting the area under the curve from A to B of the bottom function, g of x. Okay, and by properties of integrals, the difference of these two integrals is actually equal to the definite integral from a to b of f of x minus g of x. So basically, when we're finding the area between two curves, we're going to evaluate the definite integral over the interval of the top function minus the bottom function. And sometimes on that interval, the top function and the bottom function will switch, or there may be a different top and bottom function, and we might have to split up the area a little bit to find the total area between the curves. But we'll look at some examples that address that. So we're going to be using, I'm going to let you guys use your graphing calculators to help you determine or get a better picture of the area that you're calculating, and to determine which function is the top function, which function is the bottom function. So for these examples, in class, we actually graphed together, but since that would be hard to do in a video, I have screenshots of what your calculator should look like, and also a picture of the window that you could use in order to see the graphs. But you kind of have to play around with it to be able to see on your graphing calculators the areas that you want to find. Okay, so for this first function, we want to find the area of the region between the graphs of f of x, which is x squared minus 4x plus 10, and g of x, which is 4x minus x squared. So this top function in blue is f of x, and then the bottom function here is g of x. And we want to find the area between the two graphs on the interval from 1 to 3. So 1. So we want to find this area here. Okay, so to do this, the area will be equal to the integral from 1 to 3 of the top function, which is f of x, minus the bottom function, g of x. So before we integrate, I'm going to simplify or combine like terms. So 2x squared minus 8x plus 10. Okay, so now it's just evaluating the definite integral. We'll have, what is that, 2/3 x cubed minus 4x squared plus 10x. And then by fundamental theorem of calculus, this equals 2/3 times 3 cubed minus 4 times 3 squared plus 10 times 3 minus the quantity 2/3 times 1 cubed minus 4 times 1 squared plus 10 times 1. So I'm going to pop that into my calculator. And I get 16/3 as the area between f of x and g of x on the interval from 1 to 3. Okay, so we can find the area between two curves even if one of the functions dips below the x-axis, so is not positive. So for example, let's say here's our function f of x, and g of x is down here below the x-axis, so the y values are negative. On the interval from a to b, and we want to find this area here. Well, thinking back to section 6.4, let's call the area between the x-axis and f of x area 1, and then the area below the x-axis and above g of x is area 2. So if we're thinking from 6.4, area 1 would be the integral from a to b of f of x. And area 2, because it's below the x-axis, I would have to multiply the definite integral by -1. So it would be -1 times the integral from a to b of g of x. And we can see that the total area would be area 1 plus area 2. Well, area 1 is represented by the definite integral from a to b of f of x, and then area 2 would be minus the definite integral from a to b of g of x, which by properties of integrals, this is a to b of f of x minus g of x. Okay, so here we want to find the area between the graphs of f of x and g of x over the interval from -2 to 5. Well, f of x is the parabola in blue, and g of x is the line that has a y-intercept of -12 and a slope of 1. Okay, so we want the area over the interval from -2 to 5. 1, 2, 3, 4, 5. So this area plus this area. Now, over that interval, it looks like f and g switch for which is the top function and which is the bottom function. So that means that we're going to have to split this up, this area up into separate areas to calculate and then add them together. So we'll have this first area where f of x is the top function, g of x is the bottom function, and then this second area where it looks like g of x is the top function and f of x is the bottom function. Now, it would be a good idea. It looks like this point of intersection where they switch is at x equals to 1, but it would be a good idea to find the point of intersection on your calculator just to be sure. So remember, you can do that by hitting second and then the trace button, and number 5 is intersect, and you want to move the cursor so it looks like it's as close as possible to that point of intersection and hit enter 3 times so that you can just confirm that that is the point of intersection on your calculator. And then same thing, it looks like over here that the two functions intersect at x equals to 5, but you could just confirm that using your calculator. So the total area between those two curves is going to be area 1 plus area 2. So let's write an integral or set up an integral to calculate this first area. So it's going to be from -2 to 1 will be the limits of integration, and then the top function is f of x. Oh, minus 5x. And then minus the bottom function, which is g of x. Okay, I can clean that up. And integrate. Okay, then by fundamental theorem of calculus, okay, I'm going to put that into my calculator. And I get 27. And then for the second area, I'm going to integrate from 1 to 5, where the top function is g of x and the bottom function is f of x. So it'll be g of x minus f of x. And then when we integrate, remember, I'm going to let you guys use your calculators, but I'm expecting you to show all of your work by hand. Okay, so for the second area, I get 32 thirds. So then 27 plus 32 thirds is 113 thirds. Will be the area bounded between those two curves on the interval from -2 to 5. Okay, so this question is slightly different because we're not actually given the interval that we're finding the area over. So instead, we are given 3 functions, and we want to find the area of the region that's bounded by the graphs of those functions. So in blue is the function y equals to 8 over x squared. And then in red is the line y equals to 8x. And in pink is the line y equals to x. And we want the area in here. So the x-axis is going by ones, and the y-axis is also going by ones. Okay, so to find this area, notice that it looks like the area is from 0 to 2. However, it changes, it looks like, over that interval for which function is the top function. So it looks like from 0 to 1, but we can confirm this by finding the point of intersection of 8 over x squared and 8x on our calculator. But it looks like there's a point of intersection at x equals to 1, which means we're going to need to split this into 2 areas. And if you do find the point of intersection, it is, so the point 1, 8 is that point of intersection. And then here, the point 2, 2 is the point of intersection over here. So you want to make sure you do that. And then 0, 0, it's easy to see that the origin is the point of intersection for the 2 lines. They both have y-intercepts of 0. So total area, again, is going to be the sum of those 2 areas. So the first area we'll be able to find from integrating from 0 to 1. Top function is 8x, so 8x minus the bottom function x. So 7/2 x squared, from 0 to 1. So that's just 7/2. And the second area, I'm going to integrate from 1 to 2, it looks like. Top function is 8 over x squared. And bottom function is x. So I'm going to rewrite 8 over x squared as 8 times x to the negative second power, so I can use power rule to integrate. So I get negative 8x to the negative first minus 1/2 x squared. So that'll be negative 8 over 2 minus 1/2 2 squared minus negative 8 over 1 minus 1/2 times 1 squared. Okay, and I get 5/2. So we'll get 12/2, which is 6 for the area, the total area. Okay, so here we also want, we're not given an interval, we want to find the area of the region enclosed by the quadratic y equals to 2 minus x squared and y equals to negative x. So we want this area. Okay, so again, use your calculator to confirm points of intersection, but just eyeballing it, it looks like you could also find points of intersection algebraically by setting the equations equal to each other and solving for those x values where the y values are equal. Or you can use your calculator. So it looks like at negative x equals to -1 is a point of intersection, and then at x equals to 2 is a point of intersection, but you can confirm that doing second trace intersect on your calculator. Okay, so let me label the function. So in blue is f of x, and then in red is, oh no, they're not named f of x. In blue is y equals 2 minus x squared, and then in red is y equals -x. Okay, so for finding the area, it looks like we're just going to have to integrate from -1 to 2, and that the parabola 2 minus x squared will be the top function over that entire interval. So we'll have -x squared plus x plus 2 after we simplify. So -1/3 x cubed plus 1/2 x squared plus 2x. And then by fundamental theorem of calculus, so we get 4.5 or 9/2. And from your understanding of the graphs of these functions, you guys know that there will not be any other points of intersections. So for a line and a parabola, they can have at most 2 points of intersection, and we can see those in the window that we have here. Okay, so this example is slightly different as well. So we want to find the area of the region in the first quadrant that is bounded by y equals to the square root of x. And bounded by y and below by the x-axis and the line y equals to x minus 2. So in green is y equals to x minus 2. And then for the x-axis, I can represent the x-axis as the horizontal line y equals to 0. So I have that graphed on here. So that means we want to find this area. Okay, so it looks like, well, actually we can see, we know that there's an x-intercept for the line y equals to x minus 2 at x equals to 2. So at x equals to 2, y equals x minus 2 becomes the bottom function, versus from 0 to 2, it looks like the horizontal line y equals to 0, which is the x-axis, is the bottom function. So we're going to have to split this into two areas because the bottom function is going to switch. It looks like y equals to the square root of x stays the top function on both of those intervals. And confirm that x equals to 4 is the actual point of intersection of x minus 2 and root x. You can do that either algebraically or you can do it using your calculator. So total area will be A1 plus A2. So the first area, I'm going to integrate from 0 to 2 root x minus 0. Well, that's easy. That's just going to be integrating from 0 to 2 x to the 1/2. So we get, that'll be 2/3 x to the 3/2. And that'll be minus 0. So what is that? I should just do this by hand. Okay, so we could even, so if that's 2 to the 2, so that's going to be 2 to the 5 halves, right? If we add 2 to the first power times 2 to the first power times 2 to the 3/2. If we add the exponents, that would be 2 to the 5/2 over 3, which is approximately is approximately 1.886. Okay, so that's the first area. And then the second area, we're going to integrate from 2 to 4 top function minus bottom function. So 2/3 x to the 3/2 minus 1/2 x squared plus 2x. I think I'm going to run out of space. So it's going to be minus 2/3 Okay, so we get okay, so it's going to be approximately 1.448, which as an exact value will be, what is that? Square root, so 2 cubed is 8, so 16/3 minus 8 plus 8 minus 2 to the 5/2 over 3 minus 2 plus 4. Okay, so let's see. 8s will cancel. So 2 plus. So that's 22/3 minus 2 to the 5 halves over 3, which can just be written as a single fraction. But that's approximately 1.448. So total area, oh, this will work out nicely. So I'm going to write this as 2 to the 5 halves over 3, and then it'll be plus 22/3 minus 2 to the 5 halves over 3. So really it's just 22/3 is the area. Okay, so this is section 6.5.